Suppose we have a metallic box which is a cube of side length L. So this is a cube of length L which is made up of metal, and suppose that inside this cube we have electromagnetic radiation at temperature T. First of all, we want to count the number of modes of this electromagnetic radiation in a given frequency range. By number of modes, we mean all independent solutions, of the wave equation, corresponding to the electric field, and the wave equation is del square E equals 1 by c square del square E by del t square. This is the wave equation corresponding to the electric field. A corresponding equation also holds for the magnetic field, but it is enough to consider only the wave equation corresponding to electric field, because the other solutions corresponding to other equation, that is the one corresponding to the magnetic field, are not independent of the solutions corresponding to this equation. We also want these solutions to satisfy that the divergence vanishes, because we are assuming that there is no charge inside this box. So we want to find all independent solutions of these two equations subject to boundary conditions. So boundary conditions that we want to satisfy is that E, that is the electric field, either vanishes on the walls. So on the walls of this box, inside this box, we want the electric field to either vanish or electric field must be perpendicular to the walls. So electric field should either vanish on the walls or it can be perpendicular to the walls. So with these boundary conditions, these two equations have following solutions. For any triplet of integers n1, n2, n3, we can write a solution of the form in the I direction, x direction, E naught cos n1 pi x over L sine of n2 pi y over L and sine of n3 pi z over L. Then in the j direction, let us call it E1 instead of E0. In the j direction, E2 cos of n2 pi y over L sine of n1 pi x over L and sine of n3 pi z over L. And then in the k direction, E3 cos of n3 pi z over L sine of n1 pi x over L and sine of n2 pi y over L. It can be checked that this electric field given by this equation satisfies the wave equation. So this wave equation is satisfied by this type of solution. We can take the time dependence, we can multiply this whole solution with time dependence, which is of the form exponential I omega t. Here omega is 2 pi nu. So it is easy to check that this solution satisfies the wave equation, provided n1 square pi square by L square plus n2 square pi square by L square plus n3 square pi square by L square is omega square by c square. So if this is satisfied, if this equation is satisfied, let us call it equation 3, let us call this equation 1 and this equation 2. So if this condition is satisfied, then this E will satisfy the wave equation, equation 1. In order to satisfy the condition of divergence of E equal to 0, we need to have E1 n1 plus E2 n2 plus E3 n3 equal to 0. So if these 3 and 4, these two conditions are satisfied, then this E will satisfy both the equations 1 and 2 and will also satisfy the boundary conditions. It is easy to check that this electric field, this type of electric field, will either vanish on the walls or will be perpendicular to the walls. So the boundary conditions are also satisfied. So for each triplet of integers n1, n2, n3, we have a solution of this form. And in fact, we have two solutions, because for each n1, n2, n3, we can find two different vectors, e1 0, let us call it e1 1, e2 1, e3 1. We can find two set of vectors, e1 2, e2 2, e3 2. So for each n1, n2, n3, we can find two independent vectors, e1 1, e2 1, e3 1, and e1 2, e2 2, e3 2, which are perpendicular to vector n1, n2, n3, that is, which satisfy condition 4. So for each n1, n2, n3, we have actually two independent solutions. Two independent solutions of equation 1 and 2 with required boundary conditions. Boundary conditions. So for each n1, n2, n3, we have two independent solutions of equations 1 and 2. However, it is to be noted that these solutions are not all independent. For example, if we change n1 to minus n1, and we keep n2 and n3 to be same, then we will also need to change E1, E2 and E3, because we want E1, E2, E3 to be perpendicular to N1, N2, N3. So E1 we will need to change sign of E1 as well. So if we make N1 negative, we will need to make E1 negative as well. So in this equation, E1 will become negative, N1 will become negative, sign of cos this thing will not change, but because E1 becomes negative, it will become negative. The component along I direction will become negative. In the second term, N1 becomes negative, sign of E2 remains same, so it will also acquire a negative sign. In the third term, E3 remains same, but since N1 becomes negative, it will also acquire negative sign. So it will be simply -1 times the old solution. So changing sign of any of these N1, N2, N3, or any two of these numbers or any three of these numbers will not change the solution. So in fact, for each non-negative triplet of integers n1, n2, n3, we have two independent solutions, or modes. So the total number of modes, say between frequency nu and nu plus d nu, this condition is also need to be satisfied, and we can write equation 3 as, so if we rewrite this equation in terms of the frequency, we have n1 square plus n2 square plus n3 square equals omega square by c square times L square by pi square. But since omega is 2 pi nu, so it becomes 4 pi square nu square L square divided by c square pi square, and we are left with 4 nu square L square by c square. If we denote by 2 nu L by c, we denote this thing as R, then the condition on n1, n2, n3 becomes n1 square plus n2 square plus n3 square equals R square, where R is 2 nu L by c. So for each non-negative n1, n2, n3 which satisfies this condition, we have two independent solutions or two independent modes. Therefore, the number of modes or number of independent solutions between frequency nu and nu plus d nu is equal to, this will be equal to the volume of, first of all we will have a factor of 2 because there are two solutions corresponding to each non-negative n1, n2, n3. So 2 times volume of a spherical shell between radius r and r plus dr in the positive quadrant. So if we in the momentum space, this is our spherical shell of between these two radii r and r plus dr, and the volume of this spherical shell will give the number of modes between frequency nu and nu plus d mu. Now this outer radius is r plus dr and the inner radius is r and the outer radius is r plus dr. Why the number of modes is equal to the volume? Because each box which corresponds to these triplet of integers is of volume 1, that is unit volume. So the number of such boxes made up of these triplet of integers will, in the limit when there are very large number of modes, will simply be equal to the volume of this shell between these radii r and r plus dr in the positive quadrant. So this will be equal to twice, since we are considering only the volume in the positive quadrant, so 1 by 8 times the volume of the spherical shell between r and r plus dr, which is 4 pi r square times dr. But r, as we know, is 2 nu L by c. So we have 1 by 4 pi, r is 2 nu L by c r square, and dr will be 2L by c d nu. So this becomes pi 4 nu square L square by c square times 2L by c d nu, and this is equal to 8, 4 into 2, 8 pi 8 pi nu square 8 pi nu square by c cube and L cube d nu. So this is our number of modes in the frequency range nu and nu plus d mu. Here L cube is the volume. So if we divide both sides by the volume, we can write number of modes per unit volume in frequency range nu to nu plus d nu equals 8 pi nu square by c cube d nu, because we have divided both sides by the volume L cube. So the number of modes per unit volume in frequency range nu to nu plus d mu is given by this equation. Now once we know the number of modes, we can calculate the energy per unit volume in this frequency range. If we use classical thermodynamics, suppose we first use classical thermodynamics. Then we know that at temperature T, each mode contains energy 1/2 kBT, where kB is Boltzmann constant. But since for each mode we have both electric and magnetic fields, so each will contribute 1/2 kBT. So we'll have 1/2 kBT plus 1/2 kBT contribution coming from the magnetic component. So the energy contribution from each mode will be kBT. So from classical thermodynamics point of view, the energy per unit volume in frequency range nu to nu plus d nu will be number of modes in this frequency range times the energy of each mode. Number of modes is 8 pi nu square d nu divided by c cube, and energy of each mode is kBT. This equation, which is derived from classical thermodynamics, is called Rayleigh Jeans law. And this is not valid in all frequency ranges. It is only valid when the frequencies are low. In high frequency range, this is not valid. If we want to derive the correct behavior, correct equation for the energy per unit volume in a given frequency range, we need to make use of the quantum properties of light, and this is what Planck assumed in deriving his law. What he did is that he assumed for each frequency nu, at each frequency nu, energy comes in packets of a fixed value, which is given by h nu, where h is called Planck's constant. So at each frequency nu, we can have 0 quanta, we can have 1 quanta which contribute energy h nu, we can have 2 quantas which contribute energy 2h nu, we can have 3 quantas which contribute energy 3h nu, and so on. These quantas of light are now known as photons, but his idea was that at each frequency nu, energy comes in quantas. We can have either 1 quanta of light, 2 quantas of light, or 3 quantas of light, and each quanta contributes an energy h nu. So if we apply Boltzmann statistics at frequency nu to all these quantas, then average energy at frequency nu by Boltzmann statistics will be given by this sum nh nu exponential minus nh nu by kBT divided by the partition function. minus nh nu by kBT. So these are all, there could be zero number of quantas, 1 quanta, 2 quanta, 3 quanta, and up to infinity. We are summing over all different possibilities. So the average energy, if there are n number of quantas, their energy is nh mu, and this is the Boltzmann weight corresponding to the state in which we have n number of quantas. So the average energy h at frequency nu is given by this equation, and it is easy to calculate, and I am leaving it as an exercise. So this is an exercise, that this comes out to be h nu divided by exponential h nu over kBT minus 1. So this is the average energy at frequency nu and temperature is T, when we assume that light is made up of quantas or photons. So now this is our energy contribution at frequency nu. So energy per unit volume between frequency range nu and nu plus d nu is, first of all, we have number of modes, 8 pi nu square by c cube d nu, 8 pi nu square d nu by c cube. This is the number of modes, and each frequency, at each frequency nu, the average energy is given by this expression. So h nu divided by exponential h nu by kBT minus 1, and this is equal to 8 pi h times nu cube d nu by c cube exponential h nu by kBT minus 1. So this is the energy per unit volume between frequency range nu and nu plus t mu. If we denote this energy as du, then we have du equals 8 pi h nu cube d nu divided by c cube exponential h nu by kBT minus 1, and this is known as Planck's law of radiation, Planck's law of black body radiation.